Hi everyone. In this video, we'll go over the solutions for this week's section handout on probability and Bayes nets. Let's start with probability. In this problem, we're given a joint distribution here over three random variables, x1, x2, and x3. And each of these random variables can take on two values, which are 0 and 1. And we're asked to compute 5 probability values, given the values in this joint table here. Let's start with the first part, which asks us to compute the probability that x1 equals 1 and x2 equals 0. Intuitively, we would look at the rows in the joint table that are consistent with the assignment here. That is the second row here and the sixth row here. Because those two rows, and only those two rows, have the assignment that x1 equals 1 and x2 equals 0. But notice that this sum is just over the possible assignments of the unwanted variable, which in this case is just x3, and so we can rewrite this expression down here as the summation over x3 of the probability that x1 equals 1, x2 equals 0, and x3 equals little x3. We can expand this out because x3 can only take on the value 0 and 1, and so this is equal to the probability that x1 equals 1, x2 equals 0, and x3 equals 0, plus the probability that x1 equals 1, x2 equals 0, and x3 equals 1. And that's, as we said at first, the summation over the second row and the sixth row, so that's 0.1 plus 0.05, and that's equal to 0.15. Next, we're asked to compute the probability that x3 equals 0. Again, intuitively, we sum over all the rows consistent with x3 equals 0, which are the first 4 rows in the joint table up here. Using marginalization, we sum over all the possible assignments of the unwanted variables, that is x1 and x2, and so we can rewrite this as a summation over x1 and x2 of the probability that x1 equals little x1, x2 equals little x2, and x3 equals 0. This sum has 4 terms, one for each of the instantiations of x1 and x2, and so we take the sum over the first 4 entries here, which are 0.05 plus 0.1 plus 0.4 plus 0.1. Adding this up, we get 0.65. In the third part, we're asked to compute the conditional probability that x2 equals 1, given that x3 equals 1. If you remember the definition of conditional probability, this is just equal to the probability that both the query, which is x2 equals 1, and the evidence, which is x3 equals 1, occur, divided by the probability that the evidence occurs, which is the probability that x3 equals 1. So the picture that you should have in mind is follows. Let's say that this area here is the area that represents x2 equals 1, and this area here is the area that represents x3 equals 1. And let's say that this box represents all our possible kind of instantiations for x2 and x3. And so kind of everything outside this circle here is x2 equals 0. Everything outside this circle here is x3 equals 0. Okay, so the conditional probability says, given that x3 equals 1, that is, we're only concerned about this kind of area here inside the circle, what part of it is also covered by x2 equals 1? Well, that's just this area here. And this area is the joint, the intersection between x3 equals 1 and x2 equals 1. And so this area divided by this area will give you this conditional probability. So we can simplify the numerator, similar to how we did in part 1, by marginalizing over the unwanted variable, which is x1 in this case, of the probability that x1 equals little x1. Then we have x2 equals 1 and x3 equals 1, divided by the probability that x3 equals 1. Well, the probability of x3, that's a distribution, and so the values in this table must sum to 1. So to calculate this value, we can just do 1 minus the probability of x3 equals 0. Why did I write it out this way? Well, we have this term here. That's just what we calculated in part 2. And so we can solve for this. This sum, we look at all the rows consistent with x2 equals 1, x3 equals 1. That's just the bottom two rows here. So we have 0.2 plus 0.0. In the denominator, we have 1 minus p of x3 equals 0. That's 0.65, so 0.65 here. And so we get 0.2 divided by 0.35. And that simplifies to 4 over 7. Next is the probability that x1 equals 0, given that x2 equals 1 and x3 equals 1. Well, we can use the definition of conditional probability again, and this is equal to, in the numerator, we have the joint over the query variable x1 equals 0, and the evidence x2 equals 1 and x3 equals 1, divided by the probability of the evidence, which is the probability that x2 equals 1 and x3 equals 1. So we can calculate the numerator and the denominator pretty easily. The numerator, that's just reading off a row on this joint table. We want the row consistent with x1 equals 0, x2 equals 1, and x3 equals 1. That's the 7th row here. So we have 0.2 on the numerator. And in the denominator, we have the probability that x2 equals 1 and x3 equals 1. Well, we used that in the numerator for part 3. That gave us a value of 0.2. And so we have 0.2 down here as well. This simplifies to 1. So why is this 1? The intuition here is that we're given that x2 equals 1 and x3 equals 1. So we're just concerned about the two last rows down here. From the last two rows, we can see that x1 equals 1 will never occur due to this value of 0 here. And that's why we get the value of 1 here, because given that x2 equals 1 and x3 equals 1, it's guaranteed that x1 will be equal to 0. And lastly, we are asked for the probability that x1 equals 0 and x2 equals 1, given that x3 equals 1. Again, we pull out our definition of a conditional probability. So in the numerator, again, we have the joint over x1 equals 0, x2 equals 1, and x3 equals 1. And now the denominator, we divide by the probability of the evidence, which is the probability that x3 equals 1. In the numerator, again, we look for the row matching x1 equals 0, x2 equals 1, x3 equals 1. That's exactly the same as this one we had in part 4. So the numerator is 0.2. And in the denominator, we have the probability that x3 equals 1. Well, that's the same as the denominator in part 3. And we got a value of 0.35 here. So we have 0.35 in the denominator. And so this simplifies to 4 over 7. Next, let's talk about Bayes nets. A Bayes net is a directed acyclic graph of your random variables aligned with some topological layout, and it basically defines a set of conditional independence assumptions between the random variables. So when we talk about Bayes nets in this class, we're really going to be thinking about these kinds of assumptions that you can make and how you can effectively perform queries inside a Bayes net. But that will come a bit later. For this question, we're primarily going to see how we can naively calculate a joint probability in a Bayes net. First thing to think about is what kinds of tables are actually stored in this Bayes net. At each random variable, we store a local conditional probability table, which is the probability of that random variable given its parent variables. So, for example, in this Bayes net here, let's take this balanced budget node here. The balanced budget node stores the probability of the balanced budget, that is the node itself, conditioned on its parents. Well, the parent of this node, that's this node here, that's whether or not marijuana was legalized. And so the table we'll store in this balanced budget node is the probability of B given M. And this is exactly this table right here. To calculate the joint probability of a Bayes net, we're going to take a product of the entries in the conditional probability tables of each node that are consistent with the assignment that we're querying for. That is, in general, the joint probability of a basenet with random variables x1, x2, all the way to xn, is this going to be a product from I equals 1 to n of the probability of xi given the parents of xi. And if xi doesn't have any parents, then this part of the conditioning bar is just empty. Let's see an example. In this table here, we're given some of the values in the joint distribution of this basenet and asked to calculate a few of them. Let's take the first entry that we need to fill out, which is the probability of plus g, plus m, plus b, and minus c. So according to this equation, we look at all 4 nodes in the basenet and we just choose the entries in the conditional probability tables that are consistent with this assignment. So we can start with any node. Let's just pick g. The value we pick for g is p of plus g. That's because we have this plus g here. For the conditional probability table in the m node, we pick p of plus m given plus g. For the b node, we pick p of plus b given plus m. And for the c node, we pick p of minus c given plus m. So we can just read off these values, right? P of plus g, that's just equal to 0.1. I'm going to write this as a fraction, so that's 1 over 10. P of plus m given plus g, that's 0.667, so that's 2/3. P of plus b given plus m, that's equal to 0.4, that's 2/5. And p of minus c given plus m, that's 0.75, and that's equal to 3/4. So if we simplify this, we get 1 over 50, and that's what we'll put in this entry here. And for the other 2 values, we follow the same sort of calculation here. It's just that the assignment is different, and so we might need to consider different entries in the conditional probability tables. So to compute this value, we're looking for the probability of plus g, minus m, minus b, and plus c. That is equal to the probability of plus g at the g node, the probability of minus m given plus g at the m node, the probability of minus b given minus m at the b node, and the probability of plus c given minus m at the c node. And so we can look up values again. The probability of plus g is 0.1, which is 1/10. The probability of minus m given plus g, that's 0.333, which is 1/3. The probability of minus b given minus m, that's equal to 0.8, which is 4/5. And the probability of plus c given minus m, that's equal to 0.5, and so that's 1/2. And simplifying this, we get 1 over 75, and that's what we'll fill in to this entry here. And so for the last entry, we're going to do the same thing. We have the probability of minus g, minus m, minus b, and plus c. That is going to be equal to the probability of minus g at the g node, the probability of minus m given minus g at the m node, the probability of minus b given minus m at the b node, and the probability of plus c given minus m at the c node. Looking at values, p of minus g, that's 0.9, so we have 9/10. The probability of minus m given minus g, that's 0.75, so that's 3/4. The probability of minus b given minus m, that's 0.8, which is 4/5. And the probability of plus c given minus m, that's 0.5, which is 1/2. And so if we simplify this, we get 27 over 100. And we'll fill that in here. This concludes the section handout solutions for this week. Thanks for watching.